Hello everyone and welcome back to another mini concept on chemistry, this time about enthalpy and reaction profiles. So this is a continuation from our last video, which was also about thermodynamics, particularly about internal energy. This time we're going to be talking about enthalpy, which is about energy as well, but more particularly about the heat energy of a system. Or if you want to be familiar with what that is from the last video, Q. You want to be familiar with Q and the behavior and the content of a system with regards to Q. So first, let's understand what is enthalpy. So as you can see here in the top, enthalpy is the quantification of the heat content of a system. Because like I mentioned earlier not earlier, but rather in the last video, we can have a system not have any forces act upon it, but heat can flow inward or outward of it. So heat can be transferred just inherently. Like let's go back to the example from the last video where we put a bottle of hot water rather, inside a bath of ice water. So there wouldn't necessarily be any forces acting on it. Rather, there would be heat transfer. And this heat transfer is what causes the resulting movement, which is the contraction or the expansion of the plastic bottle. But that's besides the point. Basically, we want to measure with enthalpy the movement of heat or the transfer of heat and describe it in a way that we're talking about how the energy of a system changes. So maybe we can visualize it easier like this. When we have a box, let's say, full of water, let's say that the water it's got an internal energy of 400 joules. Now there is enthalpy whenever there's going to be a transfer of heat. So let's say that there's heat added to the system. Heat added to the system in the form of, not in the form, but heat added to the system with the magnitude of, let's say, 10 joules. There was 10 joules of heat added. So now, the system will gain energy. And now it will become from 400 joules, we'll add 10. Our new system's total energy would be 410 joules. Now, where does enthalpy come into play here? Enthalpy is the change in the heat. So here we added 10 joules. So we added plus 10. So our enthalpy was 10 joules. This is the energy content. Hold on. This is the energy. And this is the enthalpy. It's quite easy to remember when you remember that delta means change. And you can just have H be, heat. So the change in heat. And the system originally had 400 joules of energy. And the heat, or the energy, was changed by 10 joules. So our enthalpy is 10 joules. Now how about in another situation where, hold on, let's get rid of this. Instead of having heat done to the system, or not heat done, rather heat added to the system, let's say that our system is losing energy and it releases heat. It releases heat outwards to its surroundings, 50 joules of heat. Since it's releasing, it's going to have a minus sign. So now our new overall energy of the system would be 400 minus 50, and that's 350 joules. And that's it. So our enthalpy here would be negative 50 joules. Right? And now the enthalpy is not given in just joules. We only described it this way with just joules because, it's right there. We don't really have any units to go off of. We don't have a reaction to base it off of. So this isn't exactly a thermochemical equation, right? But when we have equations like this, for example, the problem on the screen, we quantify enthalpy based on either joules per mole of a substance or kilojoules per mole of a substance. And sometimes we can have enthalpies be given to us for problems for the entire reaction. So whatever the proportion of your elements are or your compounds are in the reaction, that's how much energy it would take to have that reaction. But anyway, before we get onto that, let's describe the difference between the signs of enthalpy. So when we got the enthalpy a while ago, let's use blue. So let's say our enthalpy was minus 50 in the second one, and our enthalpy in the first one was plus 100, if I'm not mistaken. Plus 100. Whenever energy is added to a system in the form of heat, we call that endothermic. Endothermic because it's going inward. Energy is going inward, right? Endo means within. Essentially, it means within. Now, whenever it's a negative sign, that means we lose energy. The system loses energy, and what does that mean? That means it's going outward, and outward is exothermic. So exothermic reactions, they lose energy in the form of heat from within the system. Now, how do we use this to interpret reactions? Well, let's take this for example, the one here on the screen. The one in the picture. So it says here that whenever hydrochloric acid reacts with ammonium hydroxide in a beaker, the temperature goes up. So that's HCl plus NH4OH. It results in NH4Cl plus H2O. Now, the enthalpy for the reaction here is given by delta H. Right here. Now, per mole, or basically every time this reaction happens, regardless of how many moles there are, right? So let's say that we double the reaction, we will double the enthalpy. They're proportional. It says that it's negative. It has a negative enthalpy per mole of the reaction. Now, what does that tell us? We can immediately interpret what this is, what type of reaction this is, or rather, what type of enthalpy it has, because of the sign. Now, the sign, as we recall earlier, negative means exothermic. So, this entire reaction is exothermic. And how do we know if that makes sense? Well, it says that the temperature goes up. So, if, let's say from this example, this box of water releases energy, the water would get colder, so the temperature of the water would go down. But the temperature of the surroundings would go up. And that makes sense, especially here. The temperature goes up. Right? Now, complete the energy profile diagram and state whether the reaction is endothermic or exothermic. Now, here's another part of enthalpy. Enthalpy can be described using a graph. So how would we do that? Well, first, let's draw a simple X and Y. Now, here, on the left side, we would have energy. And here at the bottom, let me move the screen a bit. Here at the bottom, it would be the rate of reaction. Or, not rate of reaction, the reaction progress. Now, basically, we're describing the energy content of the system as the reaction continues, right? So, here, whenever we write a reaction profile, we start at the middle. Because the energy of a system is, in a sense, neutral. Nothing is happening yet, right? But then, at a certain point, there is an activation energy that can be added to the system in order for there to be a reaction. So basically, it's like when your phone dies and you just plug it in, but you can't immediately turn it back on. So in that sense, you need to make sure that there's just enough energy to even turn the phone back on. In that sense, here for the chemical equation, we need just the right amount of energy to make sure that the reaction actually happens. And that is what we call the energy of activation, or activation energy. Now here, it's not exactly given. We're just asked to write the energy profile because we're given the enthalpy. So how would you write that? Alright, so activation energy means there's always energy added. Right? There's energy added to the system. So there's plus H here. Oh, not H. There's plus E. Now, this E would result in an increase in energy of the system, and it would continue to be at this energy for a while until eventually it loses that energy and it either releases it or it stays that way, right? It can either gain energy and gain energy again, or it can release energy. Now, how does that make sense? Well, I'll explain after this example. So this activation energy, we'll put act. Okay, so it increases the energy of the system, and then suddenly it has to go back down. And how do we know that? It's because the total energy change of the system is negative 53.4 kilojoules. And we know that it's exothermic. And an exothermic graph always looks like this. It's always going to be lower than the original point it started. How do we interpret this? This is our enthalpy. Was negative 53.4 kilojoules. Look, it's negative because we got lower. Now, how about an endothermic reaction? An endothermic reaction would look like this. Well, it would be quite opposite. No, it would be... Excuse me. The reaction profile would look like this. Hold on, let me draw a new one. Energy. Let's just do RP. So an endothermic reaction would look like this. It would have... Hold on, let's just use one color this time. So it would have the same starting point, and then it would increase in energy, and then the ending point is still higher than where it began. So take note of the difference. Here, the overall change is positive. This is positive enthalpy because it's higher. Its content of energy is higher than when it first started. But here, the energy content of the system is lower. So what does this mean? Basically, we use energy, or we absorb energy to break bonds. We want to break these compounds together because, like, the HCl is stuck together, but we want to move it. As you can see here, right, this Cl goes to the ammonium. From hydrochloric acid, it goes to the ammonium, and then the hydroxide group, it goes from the ammonium hydroxide to the hydrochloric acid. It swaps with the chlorine and it forms water. So we want to break these bonds so that we can rearrange the atoms and then form new compounds. And in order to break bonds, so bond breakage is endothermic. Right, endothermic. And how about bond formation? Bond formation is, well, the opposite. Bond formation is exothermic. So what type of reactions are typically endothermic and exothermic? Well, it's easy to understand from this. We can just say that because bond breakage is endothermic, whenever we have more bonds broken than we actually do form, like for example, we have AB turns into A plus B, decomposition reactions are endothermic. Now, how about synthesis reactions? So let's say we'll reverse this. A plus B is equal to AB, or it turns into AB. This is a synthesis reaction. The synthesis reaction forms more bonds than it does breaking. So this is exothermic. So again, let's just indicate it here with our pen. This is positive enthalpy. This is negative enthalpy. And that pretty much covers it all for just the surface level enthalpy. So just how to describe enthalpy, how to interpret it, how to write the reaction profile, and some common reactions that show either endothermic or exothermic reactions. So I hope that is clear, because in the next video, we're going to be talking about how to solve for the enthalpy with more numbers and more computations or formulas. So yeah, that's all, and thank you everyone. I hope you learned something today, and I'll see you in the next video on bond energy and solving for the enthalpy using enthalpy of formation and more. Thank you everyone, and goodbye.